In this video, we'll talk about classifying quadratic forms. First off, we can graph quadratic forms by thinking of them as functions. For example, if I have the quadratic form q equals x1 squared, what I can do is think about this as a function f of x equals x squared. And we know how to graph that. We can draw our xy plane and draw our graph as the parabola. If I have the quadratic form q equals, say, negative 2x1 squared, then that's going to look like an inverted parabola. Now, if I have a quadratic form with more variables, say q equals x1 squared plus x2 squared, then I can draw this in 3 dimensions, and the shape that we have is a paraboloid. And if I have a quadratic form like q equals x1 squared minus x2 squared, then we have a hyperbolic surface. What you may have learned in calculus is that these surfaces have saddle points in the middle. Now, one way to classify these quadratic forms is by the signs of the output when you plug in various points for x1 and x2. We say that a quadratic form q of x is positive definite if q of x is greater than 0 whenever x is not the 0 vector. So for example, q equals x1 squared here is positive definite because our parabola lies above the x-axis. All of the outputs are positive whenever you input something that's not 0. Our paraboloid here, q equals x1 squared plus x2 squared, is also positive definite because our paraboloid is above the xy plane. We say that a quadratic form q of x is negative definite if q of x is less than 0 for all x's that's not the 0 vector. So for example, q equals negative 2x1 is negative definite because our parabola here lies below the x-axis whenever your input is not 0. Finally, we say that the quadratic form q of x is indefinite if q of x has both positive and negative values. So an example of that is our hyperbolic surface q equals x1 squared minus x2 squared. On these tips, we have that the output is positive, while down here, the outputs are negative. Now, we also have a few other terms. For example, we say that a quadratic form is positive semi-definite if q of x is greater than or equal to 0. And we say that a quadratic form is negative semi-definite if q of x is less than or equal to 0. Now, it turns out we can classify these quadratic forms by writing q in the form x transpose times a times x, and finding the eigenvalues of the symmetric matrix A. If q can be written as x transpose times a times x, where A is a symmetric matrix, then we say that q is positive definite if and only if the eigenvalues of A are all positive. Q is negative definite if and only if the eigenvalues of A are all negative. And finally, Q is indefinite if and only if A has both positive and negative eigenvalues. We won't be going through the details of the proof of this theorem, but essentially what it boils down to is making a change of variables for Q so that we rewrite Q without any cross product terms. Once you make your change of variables, Q will look like lambda 1 times y1 squared plus lambda 2 times y2 squared, and so forth, plus lambda n times yn squared. Now, if all of the eigenvalues are positive, then each of the coefficients lambda 1 through lambda n are positive, and so your quadratic form will be positive. Similarly, if all of the eigenvalues are negative, then the coefficients in front of y1 squared through yn squared are all going to be negative. So whenever you input something, you're going to get a negative output. And if you have both positive and negative eigenvalues, then it's possible to get positive and negative outputs. And finally, as a quick example, let's revisit the quadratic form we looked at in our last video. Q equals x1 squared plus 4x1 x2 minus 2x2 squared. We found that this quadratic form has the matrix A equals 1, 2, 2, negative 2. And we found that the eigenvalues for A are lambda equals negative 3 and positive 2. So since A has both positive and negative eigenvalues, we can say that Q is indefinite. So that's it for this video. In our next video, we'll talk about constraint optimization.